Okay, so getting started on our second Hell Week, going through the Univariate analysis of Seaborn, and I think this is a really good class. I think of these like really just a big walkthrough of everything there is in Seaborn, and I tried to provide as much detail as I can. Really, the most important things are a lot more than just the most important things. The reason being is you're hopefully not. I mean, it would be nice if you could remember all these things. It would be tough to remember them. You're gonna hopefully save these classes in, especially the Hell Weeks, in a nice organized place in your Google Drive, somewhere on the cloud. So as you're working, you have a quick, easy access point to go find. Oh, Brandon did this really cool thing in this class, or oh, I learned this really cool thing in the Data Analysis Bootcamp, and I want to come back to these and ChatGPT is really quick, but this is hopefully a little bit of faster way just to access that information and come back to it. And you eventually want to get to the point. Always make sure you're typing out ChatGPT or my stuff. You want to make sure you're typing it out so that you can use your fingers to help you remember. Right. So you don't want to be how would you put it? Copying and pasting everything because you're just never going to remember everything. So it's really just part of the practice, but don't think it's anything wrong with referencing. It's hard to remember everything. So and you're always going to want to try something new. So going out to the internet, Stack Overflow back in the day, ChatGPT now, my stuff, or the Data Simple classes. We really want to just ingrain it in our fingers so that it gets locked in our memory in a much lower place in our memory by using rote learning, repetition learning, but with the physical movement of typing. And it really does get locked lower. They've studied this and actually put in a lower place in your memory and is then just easier to recall from then on. And that's kind of why, like, with talking, it sounds like the words are just falling out of your mouth, but you've learned to talk through rote learning, but the muscle movements in your mouth make it easier to recall the next time. And we can use that same technique in Python, right? So you use the muscles in your finger to help you remember these things. Our human brain, it tends to be stupid to remember all of the massive amount of things we need to learn. Okay, so let's get started on the Seaborn data analysis and the univariate analysis. So we're going through student performance data set today, and we're going to go and look at the math scores, reading scores, and writing scores of different individuals. Gotta make sure I got these things in order. um, of these things, and we want to really see the math scores, reading, and writing scores of different categorical data. So we have test, preparation, lunch, parental level of education, and race, ethnicity. Okay, and then a gender as well. Okay, so we'll expose. We have 1,000 rows and 8 columns, and we have mostly object data types, mostly categories in this sense, and then integers as well. Okay, so just dot describe, just take a quick little peek at it. And what I did here is I put the categories in a list, and I went 4 categories in categories. I'm going to put the category and select it from the data frame, and then print the value counts, and then print it. Really, you could put any symbol here. It really doesn't matter. I like to be a little bit different and do something a little bit more fun. You could do, I think how I was originally taught this. I like to be different and use the alt code, I can't remember what it was, alt 56 or something like that to do one of these symbols, the spade, just a little bit different because why not? You get a little bit bored with these things. And then timesing that by 30, so it's just gonna make 30 of those. And just some definition. This, I don't know if it's important to do in the true sense in this exact format, but we really want to understand our categories and the amount of times or how many are in each one. Right, so here we have 5, 6, 2, 2, and another 2 right here. We'll see, and we'll spend some time talking about how it can be kind of difficult to deal with too many categories with Seaborn. Seaborn is a great tool and allows us to inspect our categories on a very high level into a lot of detail, but it can be really busy and kind of destroy any value that we get from the plot if we do too much. Okay. So here, starting off with our bar plot. Okay. So here what we can do is we can do a value counts. Just what that does by default is produce female and male. If we go dot index on this, what's going to happen is we're getting a list of the index, the female and male, ordered in from least to the least occurring to the most occurring. And so what I'm doing, because this is the index and this is the data in the row, that's my integer, my data type is an integer, because female, or the 518 and 482 is the data. This is just the index value. Okay. But if I want to get the index, I'm gonna put that on the X value then, female and male, and then I'll put the actual data then on the Y and plot this kind of nicely and just make a nice little box plot. Okay. You can do the same thing with mean right here. So we're gonna pull the mean from the data frame. And I'm just noticing here doing the figure like we did with pandas, although we don't have the option directly available in Seaborn. Seaborn is meant to work in the same way. It's matplotlib. So if we want to do formatting, change the title, change the figure size, we usually have to write an extra line to call it separately, but it is meant to work that way, okay? Because it is essentially matplotlib. Okay, so we go plt.figure, fig size 4 by 3. Again, selecting df mean, we're selecting the index the first time, and then y, just the values in the average right here, so df mean. Okay, and plotting it with the palette that I have above. And nice little corner, we get a nice bar plot. Okay, can do that a little bit more. And notice here that I'm assigning it to AX object. We go ax.patches again. This is a matplotlib functionality. This gives us a list of the 3 patches. So patches are really the stuff inside of a plot. So here it's the boxes in the box in the bar plot, the bars in the bar plot. So I pull those out. What I can do is I can iterate through that. So for bar in AX patches, bar set line width 3, set edge color black. I get a nice, I think it adds a lot of texture to this. This is fine. I like this a little bit better. It's just for some reason a little bit more visually appealing. I'm gonna add a title afterwards. Okay, again using matplotlib to do so. I'm showing a little bit of fun that we can have with this. All I'm doing right here is I'm changing the X and the Y. That's how we would change the vertical or horizontal type of plot that we wanted to generate, is simply by changing which is in the X and which is in the Y. Okay, and we can also do this in a more in a sense and get a little bit more statistics from this. If we don't just have the summary statistic to plot, we can plot by default the average of our whole column. So we're going to data equals df, y equals one column, x equals another column. This is a category by a continuous variable. So it's going to group by the category and give us, through bootstrap resampling, give us a confidence interval of what the average is really likely to be. Okay, so this gives, if there's a really big black line, this error bar, we have confidence that the average is likely to be changing depending on how we've resampled the data. If it's very tight, like we see here, with lots of confidence that this would likely continue to be the average for females and males, regardless of the sample size we took. Okay. Getting into the line plot. And just noticing here, I put the links to Seaborn plots here as well for you all to look and go to the documentation. I included lots of stuff. There's definitely more stuff in the documentation. Good to get comfortable looking around Seaborn, and there's a whole bunch of stuff on their website as well that you can play around with. Okay, looking at a line plot here, data equals df, x equals reading score, y equals math score, and by default, again, using bootstrap resampling to give us a little bit of a confidence interval here to give us an understanding of how, if the data was slightly different, where could that line potentially be? Okay. And then here, if we wanted to turn that off though and just do straight lines, we go error bar. So instead of confidence interval, it used to be confidence interval. CI, they've changed it to error bar. Not too long ago, truthfully. And so error bar equals none. And yes, there's a nice straight line, pretty simple. We wanted to use the hue argument, so again, reading and math, sorry. And if we wanted to use the hue argument, let's try it with a continuous variable. Okay, so as you can see, it's super busy. It automatically breaks it into 6 different bins. You can't really see anything here, right? It's really hard to tell what's going on. It maybe art looks beautiful in some senses, but it's not very valuable in a statistical analysis. So let's try another category variable with only 5 this time. It works well. Maybe a little bit better. You're starting to see sometimes the group E is a little bit higher here. It's spiking a little bit. You're getting some information from this, but it's still pretty busy, right? This is not something I want to put into a presentation. There's not a lot of value you can extract from this. So let's try it with a different category. It's tempting of a hue gender, so it's only two categories now, or two classes in our category, which is a lot better, right? So this is a simple plot, but again, too much data in our visualization can be very difficult. So here, just looking at two different colors, and we can see it right here. Getting into the hist plots. Okay, so we can do df, data equals df, x equals mass score. Change the stat of this, so it's the count, or it can be the percentage as well, or the probability. Okay, so this gives us a good sense of our distribution. And as soon as I'm doing something different here, I'm taking a random numpy.random.integer from 0 to 5. So every time I were to run this plot would be a different color. So from the palette that I created up above, I'm going to randomly select a color from it. Why? Just to have fun. Get bored of the same colors every time I deal with this class. So just changing it around a little bit and having a little bit of fun with this. But just to show how the numpy random function works. Okay, so you can see here if we were to just run this by itself. I run this, every time I run this, you can see I'm getting a different index. Not index, integers, but we can use those for index, pulling a number out of the index. Okay. To the probability here, and changing probability and count are going to look fairly similar. If they're very particular, it can be a little bit different, but you would say you would generally expect them to be very similar distributions. They can be slight differences, but be really more on a request by a boss where you want to use probability or count. One of the things that we talked about with the histogram plot is we're able to change the bins, the number of bins. So really plotting how much detail, how much noise do we want to see here? So you could say I did 30 bins. We could even turn this up to 50, and we could see a lot more detail now. We also see a lot more noise. We're kind of losing the shape of the distribution. You can see even more shapes. You turn this up to 100. It just becomes very noisy, right? And almost a little bit hard to see where that real shape is. So the benefit of looking at something like 30, not too many bins, enough bins to really get some detail, but not too much to really lose sight of what the overall shape of the distribution is. It's a normal distribution with an outlier on the left-hand side that we might need to truncate or treat in some way. Okay, and another cool thing that we can do is we can change the element to step away from boxes. We can change it into steps, so it just gives a different kind of feel. The same idea of the plot, a little bit of a different feel now. Or we could change to poly. So change that right here. So poly, and we can get a sense of this. Is not I prefer to use when we're going this way. I would prefer to use the kernel density estimation plot, but you'll see that in a few seconds. It can be quite handy to do this though. Okay, and looking into one last feature right here, we're going to do the cumulative equals true, and that's going to give us a cumulative distribution and let us know how much data has come up until this point. So for 80, mass score of 80, roughly about 800 rows had a score less than, and the rest would have above. It's a great technique to, when you use this to inspect the distributions, to really see how they evolve kind of on that tail a little bit differently. Using it just by itself when there's 6 different categories here, it's a little bit busy and hard to see. So what we can do is we can use KDE equals true and plot these and really plot the lines. We can do a little bit more to make this a little bit more useful. And so here we're going to do line KWS. And so this is really good practice doing something more complicated in Python. So we're going to pass this to an, because really what makes this line is the line plot. So we're going to pass this function to the line plot, and histplot is going to take control of this and say, hey, line plot, here's this. When you have the LW argument, change it to 5. So we can make our line plot, and this is good control, passing a dictionary to a function to control a lower level function. And it's a pretty common way, stuff you'll see quite often in Python in general. Okay. We can also change things like the multiple. So do we want layered or stacked? Okay, so just looking at two distributions and 2 categories now in this distribution, see how those change right here. And we can do, if we want to do layers, they're just right on top of each other, they're layered on top of each other, or are they stacked? Okay. And it really depends on how much detail you want to see. They can be interesting. I think the stack could be good when you have a lot of categories as well, to really see more information about each one of those categories. Getting into the KDE plot now. This is again a super simple plot, and it's just going to highlight the outside edge of our distribution. It's going to use a fairly complex machine learning algorithm to do the smoothing and essentially assume the point in between data. Where would the data be? Kind of like this rolling average. So we can do things like fill equals true. And notice here, what I'm doing is I'm turning the bandwidth method down, just like a little bit more texture on the actual data that appears in my distribution. I can turn it down even more and just get so much more data, which I don't know, it's too busy, right? Like you can see a lot of detail there. Kind of hard then to inspect this by so many different categories. So we have to be careful with how much detail we want to see. Turn this back up and we can see that this works really well. We have 5 categories and we're able to really get a good sense of each distribution in this plot now and how those evolve, and are they similar, are they different, and does this category or do one of the classes in the category like this group A seem to have a very different distribution than the rest of the categories in this class, or sorry, the classes in this category. Getting into the box plot, talked a little bit about this last time. So we have the interquartile range, so from 25th to the 75th percentile. The whisker goes 1.5 times the interquartile range, and then anything beyond that would be the classic definition of an outlier. Okay? So generalizing the whole distribution to focus on those outliers right there. Okay. Very simple to inspect this by categories. We can go x equals reading score and then y equals categorical variables. So we're going to group by then the y-axis, the category here. We can do a line width equals 3, just turn up the line width on the outside, make it look a little bit nicer. And I think it looks a little bit nicer when you do that. We can change the whisker to, instead of go 1.5 times, go up to 3 times the interquartile range to cover all of our outliers. Or you could do something a little bit smaller and do only half of that, half of the distribution, so kind of one side of this box, and really show that there's lots of outliers. It depends what you want to do in the distribution. Maybe go 2 times and see if we get any outliers. So really just highlight one or more outliers in this distribution. Getting into the violin plot. Okay, so by default, it's showing us the KDE plot on both sides, and that is supposed to be good for us humans because we notice symmetry really well. So we notice the symmetrical sides of this. It makes it easier for us to see the KDE plot in the parallel like this, the mirror image of it. Okay, I would say that that's not really the specific way that I use it. I normally use it with the split equals true. So we're going hue equals a category here. We're going to split equals true. And so if we don't use the split equals true, just to show you what this looks like, we're separating here on the x-axis by category, and then the hue is by another category. So we're just going to make 2 individual violin plots for the hue. But let's just split it up so that it shows on either side, a little bit less busy. It kind of shows either side of this. And this is really where I think this works really well, because our eyes notice symmetry really well. And so we can very easily see when things are not symmetrical. It's a really good way to compare that binary distributions and really get a good contrast of the two. Show some other things that we can do with this. We can do the inner equals quartile, which shows us the same thing as a box plot, the 25th and 75th percentile, and the median in here as well. Okay. And then we can also we can play with the bandwidth because this is a kernel density estimation. We can play with BW equals 0.2, start to get a better sense of where the actual data is that's affecting this distribution. And just to show we can have a lot of fun, we can go inner equals stick, and this is going to show exactly where each data point is, and then bandwidth equals 0.05. Kind of looks like a ghost, I guess. It depends what you feel like, but to me it kind of looks like a ghost, a weird kind of, very artistic. I don't know if you'd want to use this, but just to show all of the fun that we can have with Seaborn and all the flexibility we have in making our plots. Okay, box and plot next. So pretty simple to use. Data equals df, and then one continuous variable at either x or y. And show you this. So this is going to go the interquartile range, and then so 75th, 80th, 85th, 90th, 95, 100, or 100% of the 1.5 times the interquartile range, and then anything on side of that is considered an outlier. Okay, so we can still use this to inspect the outlier, but we can better understand how it evolved, how it got there, right? You have very truncated distribution, really kind of stubby nose distribution, and you see a little bit of outlier on the outside, you're kind of, well, maybe that's not so bad. Okay, but if this evolves slowly to this, you can really start to see, I would define these are very far away from really any data right there. They're very thin as we get out to this line. Gives you more confidence in what, you know, if that really is an outlier that you're seeing. If that really is how you want to define it. We don't want to focus on the outliers. We can go show outliers equals false and essentially turn off the outlier dots. Okay. Do the same thing up above as we saw. We can change one of the axes. We can do a continuous on one and a category on the other. So we're grouping by then this continuous variable right here. Kind of cool. And we can start to really see how these are evolve quite differently between the two. Okay, we can show the amount of area. And so what the area does is going to show us how much it's trying to represent how much data is actually in these squares, right? And so it's going to give a better sense of really how this is evolving down. Not really just a long tail, but now it's kind of the size of this. You can see these are quite thick, are really representing how much data is here, how much data is in each one of these, not quartiles, but the 5 percentiles that we have in each one of these boxes. Okay, we can also do things like area, or we could try proportion here. So yeah, we could try exponential and get a sense of really kind of nice if you really want to show how this evolves very slowly, or put the exponential rate relationship in this sense, like really defining it, how much data you can really see, really kind of illustrating that this tail is really thin as you'd evolve to the outlier. So it really depends what you're trying to showcase and which one you want to use. Okay, getting to the swarm plot. This is a really amazing plot because it allows us to inspect in such a high level of detail. Okay, so here doing x on a continuous variable on x and a categorical on y. Okay, and just putting two colors from my color palette up above and seeing that we get this. And so really you can see there's a little bit of truncating or a little bit of bunching up on the sides here. Maybe that's not really what we'd want. So we can play with size. We can turn size up to 10 and kind of defeats the purpose. We get so much overlap now that it's not super helpful in our plots. Okay. What we can do here is instead go size equals 4, and you can see you get a much, not smaller, but a much smaller dot. And so you're really able to, now it's able to plot exactly where every single dot is, every single data point is, and really allow that very high level detailed analysis, and it's true form. Just show me exactly how the data is. Don't generalize, don't hide anything. I just want to see everything. We can also change the hue argument. So we can also change the hue argument in this, and then change every single data point by the hue. And I think what's kind of something interesting. We haven't noticed this before, but we see the female. We saw the distribution going down to one side, but because of the generalization of the histogram or the KDE, this is kind of hidden, right? It looked like it went down. You didn't see this bunch up at 100 right here. So there's lots of the females, specifically that ate the standard lunch, a couple that ate the free lunch, but mostly the standard lunch, and they got perfect scores. And it kind of just, it doesn't evolve to that. It kind of just tapers off until a whole bunch got truncated at the top of the 100 scores. So some very smart girls in this school, but that was hidden in every other way. So this allows for a lot of detail, and you can see a lot of people that got scores right close to the 60 mark. We want to understand maybe why that is. Some people are just passing or just close to passing, almost got there but not quite. And good to understand really what's going on in this sense. But this again, this high level of detail, again, allows you to come up with theories and continue your inspection. What else? Okay, so I want to understand maybe these girls that here were passed. What's something that's similarity that I could find about this group? Maybe the same race and ethnicity, something more, right? So these plots give you kind of an idea of what else to investigate. Count plots. So count plot's pretty simple in the sense that it just counts the frequency, the number of times a category appears in our data. So female a little bit over 500, male a little bit under 500. We can look at a category with more classes in it and get a sense of how imbalanced, if it is imbalanced or not imbalanced. Looking at this, and so we can see really that group C is really highly represented, whereas group A is very underrepresented. Does that matter? Well, it might, right? So it depends on your situation, so something to be aware of. Just to show this, like I showed up above, we can look at the index values of the value counts. So if I do dot index on the value counts, it's going to give me the value counts from C, D, from largest to smallest. Right? So it's putting it in order. So I'm going to save that labels. And when I go order equals labels, it's going to then plot these in the ordering that I determined. Oops, I'm going to make sure to run things in order. And so now we have them going in descending order, or we could even switch that around if we want to. Looking at another color here, what we're doing is lunch equals X. So we're putting that on the sides and really getting a count of each one of these in our count plot. And then the palette colors here, we're going to change the hue by the gender so we can understand how that plays into this category. So we get some ability to inspect a category by a category. If we wanted to add this dodge equals false, so they're not side by side, put them on top of each other, really to highlight what is, what happened or which category is represented the most. Okay, we can look at our figure level plots next. The Seaborn dis plot allows for a lot of detail in terms of the categories and how we can kind of cross section and find the subcategories distributions and really start to understand how important these categories are in understanding the distribution. So data equals df, continuous variable x, kd equals true, and then random color palettes. Okay. And here what I'm doing is kd equals true, column though equals gender. So now we have the female and then the male distributions for, again, the math score. Next, we have the math score, kd equals true, column gender, row equals lunch. Now, inspecting this by subcategories, really looking at to see how those distributions are different. And you can see quite a bit different, truthfully, when you see there's a lot of bunching up right here in the middle for the female that ate the standard lunch, but the female that ate the reduced lunch, it's almost like the weight is a lot more to the left, right, if they ate the reduced lunch. Same thing with males, right? So important to eat, I would say eat before you write your exams. And this is a good kind of evidence. We're starting to get that same common sense argument right there. Extending this even a little bit further, we can run against the colors are a little bit different. Random colors, you get sometimes they're the same random color. And here what we're doing is we're looking at these two distributions by row, column, and then by hue to change the color and really getting a sense of how test preparation would be impacted by these two. And you see males did really, really well in terms of math scores in the free lunch male, and then they did really well for test preparation equals completed. That's when they did seem to do the best, right? Which makes sense. But again, there's lots of detail that you wouldn't really be able to inspect in another way to such a granular level. Is it going to be important? Not on every distribution. So this would be something that you want to have a reason with your initial analysis to go this extra level. You don't usually start with the figure level plots. Okay, so the way that we can control getting into the cat plot and the way that we can control the size of our cat plot is a little bit different than what we see in the matplotlib.figure fig size equals width by height. Here, because there's going to be lots of these plots, we can use the height argument to say, I want to make my plot this high. Okay, so 3.5 here. And if I wanted to then change the aspects of my plot, and so doing the same thing here, showing just that we can do a swarm plot here. And if I wanted to change the aspects of how wide it is, I can say aspect equals 0.8. So 3.5, and I want to make that width 80% of that. So height is this, and then aspect is the percentage, or 1.1, 1.2. How much bigger on the wide side did you want this to be? Okay, and you could do something maybe here. Let's turn this up to 2, and you get something quite a bit wider in this sense. Okay. And I don't know if you needed to do that. It looks a little bit too stretched out now, but that might be helpful in actually exploring this data. And you can really see, you get a good sense of where the actual data is when you do this. Okay. We can do some other plots right here. We can do lunch equals, so mass scores lunch, column gender, hue, so separating by 1, 2, 3, and then test preparation, so 4. Only on one row right here. So you're getting a good sense of how that distribution is really changed by female and male, but really by test preparation seems to have a much larger effect on the final scores, which is not super surprising. We also have access to the point plot, which really puts the average and what is the, using bootstrap recycling, what is the expected deviation in that average, and just connecting those two together. We can also do the violin plot, split equals true, to really get a very high level of detailed analysis of our categories. And going a little bit farther, we can also do the bar plot here. Hue equals test preparation, y and x, y equals category, x equals continuous, column equals gender. So really going into a lot of detail, and then getting the sense of, you can see this confidence interval, this error bar is a lot bigger than this one. And so we're getting a sense that there's more movement in the test completed grouping than there is in the people just did not do as well with the no test preparation, right? The range doesn't necessarily mean you're going to do better, but it gives you a better chance that you're going to have a better score. Okay. So thank you for joining me today. It's really good, and I'll see you in the 5th Data Analysis Bootcamp class. See you there.